Hello, together let's look at the following argument, and we'll be utilizing the tools of propositional logic to help us. In the argument, we have the first premise, I will study algebra or watch TV. The second premise tells us that I will study logic or not study algebra, and the conclusion is therefore, I will watch TV or study logic. At an intuitive level, it does seem to be a valid argument. And if the two premises are true, then the conclusion must likewise be true. Let's consider the options here. Algebra versus TV, and logic versus not algebra. So it looks like we're going to have logic or TV for sure. However, how can we go beyond that intuitive level and prove that it's a valid argument? Now, a lot of discrete math textbooks will cover something called resolution inference. And its formal structure is as follows. So we have something like 1, P or Q, 2, not P or R, 3, therefore Q or R. And that's just by resolution with lines 1 and 2. So this is one of the inference rules that is listed in a lot of discrete math textbooks. But most standard logic textbooks don't put this on their list of inferences, and there's strictly no need to, yet we can derive it. And by the way, this conclusion they call the resolvent, okay? But how can we derive it? Well, we're going to use a standard list of inferences, such as modus ponens, modus tollens, disjunctive syllogism, and so on, and so forth. So let's prove it. But to prove it, we're going to need to do an indirect proof. Also known as a reductio ad absurdum. So in any indirect proof or reductio ad absurdum, we'll assume the opposite of what we want to prove. And from that assumption, we'll attempt to derive a contradiction. And because a contradiction cannot be true, what led to that contradiction cannot be true, and so we would have proved what we want to prove. So let's do that. And so our first premise is P or Q. Our second premise is not P or R. And we ultimately want to prove that Q or R is the case. And we're going to do an indirect reductio ad absurdum proof. So the first thing we'll do for line 3 is assume the opposite of what we want to prove. So we will say not, parentheses, Q or R. And this is just an assumption. And because it's an assumption, we will place it, so to speak, under quarantine. It's just an assumption. We're not saying that's true or false. We're going to assume it and see what the consequences are of that assumption. Okay. Line 4. What next? Well, let's work on that assumption. And the first thing that should jumps to my mind, is to use De Morgan's rule. So we can get not Q and not R by De Morgan. And this is on line 3. Still under quarantine based on that assumption. We're looking for a contradiction, so we want something like P and not P. That would be a contradiction. That cannot be true. Can we derive that? I think we can. So for example, here's a P, here's a not P. So could we somehow say P is the case and not P is the case simultaneously in a conjunction? So we have this not Q here, right? So let's get that by itself, and then we can get a P from line 1, because we'll have a disjunctive syllogism. So for line 5, right now we'll just say not Q by the simplification of line 4. And now, notice line 1, P or Q. Notice line 5, not Q. So we can get P from that. So for line 6, we can get P by our disjunctive syllogism with lines 1 and 5, still under quarantine, based on that assumption. Great. We're going to want that not P from line 2. So notice that line 4, we have not Q or not R. So let's get that not R, and to be, so to speak, as explicit as possible, let's just first use a commutative rule to say we have not R and not Q. Commutative rule with line 4. And then for 8, we'll just get not R by the simplification of 7. And now we can work with lines 2 and 8. So line 2, the premise tells us not P or R, but line 8 says not R, so because we have a disjunctive syllogism for line 9, we can get a not P disjunctive syllogism, lines 2 and 8. Now notice, line 6, we have this P. Line 9, we have this not P. So let's just combine those together to 10 to get our contradiction. So we have P and not P through the conjunction rule with lines 6 and 9. So based on this assumption, line 3, we end up at this contradiction. So that assumption must be false, right? So for line 11, we'll say it's not the case that Q or R by our indirect proof with lines 3 to 10. And then we'll just apply our double negation. So we have this not, so that's just Q or R. Double negation, line 11, and therefore we've proved what we wanted to prove. Q or R is the case. Pretty neat. I think in general, indirect proofs are pretty interesting, pretty neat, because they're based on, first off, recognizing that contradictions are not true, but also they're based on recognizing the law of excluded middle, because Q or R, this statement is either going to be true or false insofar as it is a proposition, insofar as it declares something to be the case. Now, second way to prove this argument, by the way, is through a truth table. And really, any valid argument in propositional logic can, so to speak, be shown to be a tautology. We can only get true values for a valid argument. I'm not going to do that here, but I am going to show you my work for that. And here is my work for that. So we have the argument. So this is the first premise, P or Q, the second premise, not P or R. So as part of the antecedent to a conditional, and this consequent to the conditional is a conclusion. So we fill the truth table, so we have the values P, Q, R, and we go through it, and we ultimately end up at this right here. And notice, of course, that this is all true value, so it is a tautology. And that's another way to say that this argument is valid. And so if we scroll up back here, this definitely is a good argument, and we proved that through propositional logic. I will study algebra or watch TV. I will study logic or not study algebra. Therefore, I will watch TV or study logic. I hope this video has been helpful to you and interesting. I'm the Amateur Logician from amateurlogician.com. Good luck to you, and until next time.